Welcome to Thought Frontier.
Hey everyone, and welcome to another deep dive. This time, we're tackling something that's both incredibly fundamental and incredibly mysterious. Gravitons.
Gravitons, yeah. Those hypothetical particles that are thought to carry the force of gravity.
Exactly. Like, we know photons carry light, right? That's
Right.
electromagnetism.
Right.
But for gravity, it's like, well, maybe gravitons do the job, but we've never actually seen one.
It's a big question mark hanging over physics. Do they exist? What are they like if they do exist?
And that's exactly what we're going to dig into today.
Yeah.
We've got a really cool mix of sources.
Oh, yeah.
Yeah. So first up, we've got this article from Quantum magazine that takes a look at the history of light and how that weirdness relates to gravitons.
The history of light, huh? Interesting place to start.
Yeah, well, as you'll see, it kind of sets the stage for the whole graviton mystery. Then we're going to jump into some recent news from Avi Loeb.
Avi Loeb, the Harvard astrophysicist.
Yeah.
Always good for a bold claim.
Oh, he doesn't disappoint this time either. He says new research basically backs up Einstein's prediction that gravitons have no mass.
No mass at all. That's a big statement.
And finally, we're going to wrangle with this pretty dense scientific paper called Reconstructing the Graviton. It gets deep into the theoretical weeds.
Sounds like a challenge.
It is, but it also has some seriously surprising stuff in there.
Well, I'm all for surprises. Let's get started.
All right, so let's rewind the clock back to the early 1900s when physicists were really struggling with what light is. Is it a wave, like ripples on a pond, or is it particles, like little bullets of energy?
Right. For centuries, the wave theory was king, but then Einstein comes along.
Always shaking things up.
Yeah, exactly.
Yeah.
He's explaining the photoelectric effect, and he shows that light can knock electrons off of atoms. A wave shouldn't be able to do that, so the only way it makes sense is if light is also acting like a particle. He called those particles photons.
So light is a wave and a particle. Whoa, it still kind of blows my mind.
It was revolutionary. It introduced this whole idea of quantization to physics. Energy, momentum, even light itself comes in these discrete chunks, not just a smooth flow.
Okay, so here's where the graviton idea starts to emerge. If light, which seems so wave-like, can also be a particle, could gravity work the same way?
Precisely. If other forces, like electromagnetism, are carried by particles, the photon in this case, maybe gravity, has its own carrier particle, the graviton.
So the search for the graviton is basically an attempt to quantize gravity, bring it into this quantum world of particles.
Exactly. It's about trying to fit gravity into our understanding of all the other forces, finding that missing piece of the puzzle.
Okay, well, let's talk about Avi Loeb then. He's claiming this new research supports Einstein's idea that gravitons are massless.
Yeah, his article in the debrief has this really attention-grabbing title, New Research May Vindicate Einstein's Theoretical Prediction of Massless Gravitons.
So what exactly is he looking at?
Well, he's focused on how our galaxy, the Milky Way, moves within the cosmic microwave background.
The CMB, that's like the echo of the Big Bang, right? The oldest light in the universe.
Yeah. But he's also looking at the large-scale structure of galaxies, using surveys like 2MASS to see where they're all clumped together.
I'm not quite seeing how that connects to gravitons, though.
So here's the thing. His calculations show that if gravitons did have mass, the way our galaxy moves through the CMB wouldn't line up with the way those galaxies are distributed.
Oh, interesting. So because things do seem to match up, that suggests gravitons must be massless.
Yeah, and not just kind of massless. His findings suggest the graviton's mass has got to be ridiculously tiny. His limit is like 250 million times stronger than previous limits, which were based on gravitational wave data.
Wow, that's pretty convincing. So, case closed. Gravitons exist and they have no mass.
Well, hold on a second. Loeb's work is exciting, but it's based on some assumptions, like any scientific research. It's a really strong piece of evidence, but we still need more confirmation.
Fair enough. Science is all about being skeptical and testing those ideas rigorously. Okay, so I guess we're not quite ready to rewrite the textbooks just yet. But this definitely adds to the growing body of evidence, right?
Absolutely. It's a significant step forward. Now, are you ready to tackle that reconstructing the graviton paper? It's a bit of a beast.
Oh yeah, let's do it. Bring on the theoretical heavy lifting.
All right, so the goal of this paper is to figure out, well, what a graviton would be like based on this theory called asymptotically safe gravity.
And they actually talk about two types of gravitons, right? The fluctuation graviton and the background graviton.
Right, and this is where things get really strange. The paper suggests that the background graviton might have a negative spectral function.
Okay, I'm gonna need some help with that one. What in the world does that even mean?
Imagine like a sound wave, but parts of it are negative. It's counterintuitive, I know, but that's what the math is pointing to.
Negative parts of a wave? How is that even possible?
It's definitely weird, but a similar thing happens with gluons, the particles that carry the strong force holding atomic nuclei together.
So maybe it's not a sign that the theory is wrong, just that gravitons are, well, unusual.
Exactly. It could be telling us something deep about how gravity works, that it's not
Yeah.
just particles zipping around, but something more fundamental, woven into the fabric of space-time itself.
Okay, now my mind is officially blown. This is getting pretty deep. I think we've covered a lot of ground here, from the history of light to this mind-boggling background graviton with its negative whatever it was.
Spectral function.
Right, spectral function. So that's a good place to pause, catch our breath, and let everyone process all this.
Sounds good to me. There's definitely a lot to digest here, and we're just getting started.
We'll be back soon with part 2 of our deep dive into the gravitons, so stay tuned. And we're back, diving deeper into the world of gravitons. Last time, we got into the history, Avilob's research, and that wild paper about reconstructing the graviton.
Yeah, a lot to unpack there.
So let's say, hypothetically, we do find definitive proof that gravitons exist. What does that actually mean? Like, for our understanding of the universe, the big picture stuff.
Oh, it would be huge. It would mean all 4 fundamental forces, gravity, electromagnetism, the strong force, the weak force, they're all playing by the same quantum rules.
Okay, so a big step toward that theory of everything physicists are always chasing.
Exactly. A theory that could explain how everything works, from tiny particles to giant galaxies.
That's pretty awesome. But what about more practical stuff? Are there, like, real-world applications of knowing about gravitons?
Well, that's where things get really speculative.
Yeah.
Imagine if we could control gravitons, like we control photons with lasers and electronics.
Well, hold on. Are we talking anti-gravity, warp drives, like manipulating space-time?
Those are some of the more far-out ideas people have tossed around.
Far out, but cool.
Yeah. But even if we never get to that level, understanding gravitons could still lead to breakthroughs in space travel, energy, maybe even communication.
So it's not just about understanding gravity on a cosmic scale. It's about potentially harnessing it for, well, who knows what.
Exactly. But let's not get too carried away. We're still figuring out the basics of gravitons.
Yeah.
Remember, even their existence is still debated.
Right, right. Okay, so let's circle back to that reconstructing the graviton paper. There was that thing about unitarity and quantum gravity that we didn't really get into.
Oh, unitarity.
No.
That's a big one. It's basically a check to make sure our theories make sense.
Like a sanity check for physics?
Yeah. It means the total probability of all possible outcomes has got to equal 1 or 100%.
Yeah.
The math has got to reflect reality.
Okay, that makes sense. But where do gravitons fit in?
Well, the paper suggests there's a connection between gravitons and this idea of unitarity and quantum gravity. Understanding gravitons, especially that spectral function thing, might be key to making sure the math of quantum gravity works out.
So it's not just about finding the graviton, it's about understanding how it behaves, its quirks.
And as we saw, gravitons might have some pretty strange quirks. That negative spectral function is still messing with my head.
Me too. It's like, how can a wave have negative parts?
It challenges our intuitions. But like we said, gluons do something similar. Maybe it's just a weird way our math describes these forces, or maybe it's pointing to something deeper about reality itself.
Okay, deep thoughts for sure. So, what's next? Where do we go from here in this whole graviton quest?
Well, experimentally, there are some really exciting things happening. There are proposals for even more sensitive gravitational wave detectors, like the Einstein telescope and the Cosmic Explorer.
I've heard of those. They're like super-powered ears listening for the faintest ripples in space-time.
Yeah, and people are still studying the CMB, trying to find clues about gravitons in the very early universe, right after the Big Bang.
Like using the whole universe as a giant particle detector.
That's one way to think about it. And theoretically, physicists are building more and more complex models of quantum gravity, searching for that theory that ties everything together.
The ultimate theory of everything.
A theory that's eluded us for so long. But with each new experiment, each new insight, we get a little bit closer.
It's exciting to be along for the ride, even if we don't know where it'll lead. I think this is a good spot to take a break, though. Let everyone absorb all this.
Agreed. Let's gather our thoughts and get ready for the final part of our graviton journey.
Okay, we're back for the final stretch of our deep dive into gravitons. I feel like we've been through a lot. The history, the mind-bending science, those negative spectral functions.
Yeah, it's been quite a journey.
So now I'm thinking, like, zoom out, big picture.
Mhm.
What does all this graviton stuff tell us about, our place in the universe? Does it change how we see ourselves?
I think it really highlights how connected everything is. This tiny particle, if it even exists,
Yeah.
could hold the key to understanding the whole universe. It's kind of humbling.
Yeah, like we're all part of this cosmic web held together by gravity, by those gravitons.
And by understanding gravity, understanding those fundamental forces, we can understand ourselves better, our place in all of this.
It's like the more we learn, the more we realize how much we don't know, how much
Yeah.
is still out there.
And that's what drives science, right? That curiosity, that desire to explore the unknown.
Totally. So even if we never actually find the graviton, the search itself is still valuable.
Absolutely. Every experiment, every theory, every dead end, it all gets us closer to understanding how the universe works.
Like putting together a giant puzzle, one piece at a time.
And maybe the graviton is that missing piece that finally completes the picture. Imagine the possibilities if we could truly grasp gravity, its quantum nature.
Okay, now I'm getting excited again. But even without those future breakthroughs, the hunt for the graviton has already led to some amazing stuff.
Think about gravitational wave astronomy. A few decades ago, we weren't even sure those waves existed. Now we're detecting them all the time, listening to black holes collide.
It's like a whole new way of seeing the universe.
And it's all thanks to, in part, this pursuit of the graviton, this drive to understand gravity at its core.
It really shows you the power of scientific curiosity, of asking those fundamental questions, even if they seem impossible to answer.
And it's a journey that's far from over. There are still so many questions. Will we ever directly detect a graviton? Will we find that unified theory of everything?
Well, those are questions for another deep dive. But for now, I want to thank you for taking us on this incredible exploration of the graviton. I feel like I've learned so much, not just about the science, but about how science works.
It's been my pleasure.
Yeah.
And to everyone listening, keep that curiosity alive, keep asking questions, and keep exploring the universe.
Couldn't have said it better myself. Thanks for joining us. Until next time, keep on learning.